So if you like to have those kind of handy, so you can take notes on them or whatever, you might want to download those carbohydrate PowerPoint slides for Monday. Okay. Other than that, does anybody have any questions before we get started?
Yeah, just one quick question. You mentioned last week, I think, that you had ACS studies
Yes.
available. Do you have like a lot of those?
I do. Just ask me in lab because that's where they're kept.
Okay.
So just remind, if you want one, if you want to check one out, you can get in touch with me during lab, and I can get. Yeah, that's fine. All right. Well, let's go ahead. Let me start recording here just a second. All right, so last time we left off, we were talking about we had started into the condensation reactions. And if you recall, the condensation reactions are just a carbon-carbon bond forming reaction where you combine two pieces and you end up losing a neutral small molecule, most commonly water or an alcohol. And the first one we were looking at was the very famous aldol reaction. And we looked at kind of the classic way of doing that. So I gave you the kind of a part A, which was the classic aldol. We looked at something like this. And what that really resulted in the flask was just given the relative acid-base chemistry between the hydroxide and the alpha proton, you end up not getting complete deprotonation. So you end up with some enolate and some aldehyde in the flask, which translates to some nucleophile and some electrophile, and that causes a reaction. The two of them combine. And we went through the mechanism of this a couple of times at least. But ultimately what you end up with most of the time when you do these reactions is this kind of alpha-beta unsaturated carbonyl compound. Okay. The second way I gave you was how to combine two aldehydes or ketones that are not the same. And this is what we call the mixed or crossed aldol. I'm going to give you a third way now. That's where we will start today's lecture. And the third way is, imagine for a minute if we had something that looked like something that looked like that. What do you think we're setting up to do in this reaction? Exactly. We're setting this up because you've got two aldehydes here, and they're reasonably spaced, meaning they would give you a relatively strain-free ring. We're setting up to do an intramolecular aldol reaction. And so the way this would work is pretty much the same way that we have seen for all of the others. You will end up deprotonating one of the alpha positions. So you generate some of the enolate, and then this can wrap around and attack the other aldehyde. Now, just as a general rule, and you can do this or not, it's really up to you, but anytime I'm making or destroying rings, I always number my carbons. It just helps me not to make mistakes. So I'm going to go ahead and do that. Just number it straight across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116 And so what you can see is we are going to make a ring between carbons 2 and 6, as I've numbered it. So if you count those carbons to figure out what size ring that would generate, 1, 2, 3, 4, that would generate a 5-membered ring. So what I like to do for these types of problems is I don't even worry about putting all the stuff on and making it the exact product at first. I'm just gonna sketch out the skeleton of the ring. So I know I'm gonna make a 5-membered ring. There's my 5-membered ring. What I'm gonna do now is number it in the same way that I did it just a second ago in the previous step. So I've got carbon 2, 3, 4, 5, and 6. Carbon 1 is hanging off. It's not part of the ring, so it's just sticking off carbon 2 there. So that's your aldehyde, the carbon number 1 as I numbered it. What else do we have in here? Carbon 6 should be that tetrahedral intermediate, so that's going to be, it's no longer a carbonyl, it's the O-. All right, from there, just as in the previous mechanisms, that alkoxide is going to go and protonate from the water solvent. Giving you that. Well, if you look, there's the carbonyl, that would be the alpha, that would be the beta. This is a beta hydroxycarbonyl, which is one of the products that we would expect from an aldol reaction. Right? Now, just as in the previous examples, these are notoriously difficult to isolate, and usually you can't. So what will end up happening, you've still got an acidic alpha proton. It's still in base. And so that is going to deprotonate there and kick out the hydroxide. And so what we end up with is something like that, which is an alpha beta unsaturated carbonyl, which is what we expect from all of our aldol products. Now with these intramolecular aldols, you are a little bit limited. I mentioned whenever we first started this conversation that it has to be a reasonable sized ring. So what that means is it can't be a super strained ring. You're not going to make 3-membered or 4-membered rings with this, right? Typically, you're only going to make 5 or 6-membered rings. All right. Any questions on how we did this one? Mm-hmm.
Did the OH become a leaving group?
Did the OH what?
Did you say the OH was a leaving group?
Uh-huh. Yeah, the hydroxide is acting as a leaving group. Number one, you have to keep in mind that we're no longer dealing with SN2 reactions.
Okay.
And so a lot of these mechanisms, and we saw this back in the previous chapter with the derivatives, they are not as sensitive to leaving group ability, number one.
Okay.
Number two, the other kind of driving force for this, or the compensating factor, you might say, is the fact that you end up making this highly conjugated system as a result.
Okay.
So it kind of, you get compensated for the loss of a bad leaving group, number one, and also these mechanisms just aren't as sensitive as SN2 mechanisms were to leaving group ability. Yeah.
Professor, is it always the alpha hydrogen gets deprotonated?
Mm-hmm. Yeah, because none of the other hydrogens are remotely acidic.
Oh, okay.
Right, remember, the whole reason why the alpha proton is unique, and we can do all of this chemistry, is because if you deprotonate it, it can be delocalized into the carbonyl. It spreads out that electron density. And anytime you can delocalize electrons, you're all the better for it.
Thank you.
Okay, any other questions on this intramolecular? All right, so let me give you an example. You can try your hand at it, see what you get. So see if you could predict the product of this intramolecular aldol. All right, if you're looking at this one, we have a few different options because you have several different alpha positions, right? So you could theoretically enolize at the C5, that's an alpha position. You could enolize at the C3, that's an alpha position. Or you can enolize at the C1, that's an alpha position. So the question is, which one is going to enolize? The answer is all of them. But only one is going to lead to a viable product. So let's see which one that would be. If C5 were to enolize, it would wrap around and attack the other carbonyl, which would give you a 1, 2, 3, that would give you a 4-membered ring. That's not gonna happen. So that's not an option. If C3 were to enolize, it would wrap around and attack the aldehyde, giving you a 1, 2, 3, another 4-membered ring. That's not gonna happen. So if C1 were to enolize, that would wrap around and attack the aldehyde, giving you a 1, 2, 3, 4, 5, 6-membered ring. You've got a winner. So, again, I am just gonna go ahead, I know I'm gonna get a 6-membered ring from this, so I'm just gonna draw that skeleton and we can decorate it later. 6-membered ring, there we go. All right, I'm gonna number it in the same way that I did at the beginning. Let's do it like this. Okay, so what do we got? C2 is the ketone carbonyl and nothing happened to it, so it's still there. C6, if you think about mechanistically what happened here, we enolized there and it wrapped around and attacked like that. So C6 is going to be that tetrahedral intermediate. Initially it would appear as an alkoxide, which would grab a proton from the water solvent. giving us that. Is that a viable aldol product?
So it's really long.
Yeah, it would, but we know we're on the right track because if you think about what this is, there's your carbonyl, there's the alpha, there's your beta. That's a beta hydroxycarbonyl, which is on the road to the final aldol product. All right, so the only thing we have left to do is you still have acidic alpha protons in the alpha position. You're still in base. Hydroxide comes in, takes one of those protons, and kicks out the hydroxide. So we should be left with that, an alpha beta unsaturated carbonyl compound. Any questions on this one?
I had a quick thought about carbon. Do we have to worry about like the stability of like primaries, secondaries, and tertiaries with that as much as like the carbocations?
You mean like whenever you make one over here?
Yeah, if we were doing like a mechanism problem, and we were like considering carbon formation, would primaries be like less likely than tertiaries, or
Just the opposite.
the opposite?
Yeah, but more so what you're looking for is which carbanion can be best stabilized. So it's not it's not so much an issue of a primary, secondary versus a tertiary. It's more which carbanion is best stabilized. Meaning, like, do you have a carbonyl next to it? Or do you have very electronegative atoms that are inductively stabilizing it? So things like that more so than just a straight primary, secondary, tertiary type thing.
Okay.
Okay, any other questions on the aldol? All right, the next one we will go into, the next condensation reaction is also a named reaction, and this is called the Claisen. So the Claisen reaction or the Claisen condensation. So I'm going to go ahead, just like I did with the aldol, and give you the functional group transformation here. So the functional group transformation with the Claisen is instead of dealing with aldehydes and ketones, it's going to deal with esters. So it's going to take two esters and combine them, and the product that you're going to get here is going to be a beta keto ester. So, I'll show you just a really simple case, and then we'll talk about some of the specifics here. So if you imagine just a very simple ester, I'm going to take and I'm going to combine that with the base sodium methoxide. Now, actually, before we move on, I think it's worth mentioning this. Why is it here that I'm using sodium methoxide? Why didn't I just use sodium hydroxide like I did with all the aldol reactions?
You don't want to place the oscillation.
Yeah, exactly. Remember, esters are easily hydrolyzed. If I were to take this ester and use sodium hydroxide on it in an attempt to deprotonate the alpha position, you're going to get a whole lot more hydrolysis and making just the carboxylic acid, or technically the carboxylate that way. So it would give you some pretty serious complications that way. All right. So what you'll note is my base is matching my ester. Okay, that's important too. So, for instance, it would not be wise in this reaction to use, say, sodium ethoxide. Because if I were to use sodium ethoxide, imagine what could happen. If you were to use sodium ethoxide, yes, it could deprotonate and would deprotonate, but it could also attack the carbonyl. Right, come up and do a substitution reaction. Electrons go up on the carbonyl, they would come back down, kick out the methoxide, and you would end up making the ethyl ester. By the way, this is given a special name. We call this transesterification. So, and that's something we obviously don't want. So to avoid transesterification, we just have to match the base to the ester. Okay, so if I'm using a methyl ester, I'm going to make sure to use the methoxide base. If I were using an ethyl ester, I would use ethoxide base, and so on. All right. So anyway, so now that we've got the right ester and base pairing, what's going to happen? Actually, let me just make another little side note here. It's probably worth noting here that esters are not quite as acidic. The alpha position of esters are not quite as acidic as aldehydes and ketones. So just to give you an idea, aldehydes are the most acidic of the carbonyl compounds, or their alpha position anyway, with a pKa of around 19. Ketones are pretty close, but they're a little bit less acidic, around 20. Esters are down around 25. So they are not quite as acidic. And again, we talked about this a little bit last time. The reason being is because they have that oxygen heteroatom attached, which is kind of pushing electron density into the carbonyl via resonance. And so it's hard to push electron density in from the left, from the alpha carbon, when you also have electron density being pushed in from the heteroatom oxygen. And as a result, they are not quite as acidic. But in any case, we can get some enolization with these alkoxide bases. So once you add that, you're going to end up with kind of the same situation that you have with aldol, meaning you're going to have some of the molecules that don't do anything, they're just hanging out. But then you're going to have some that can enolize. So just like the aldol, once you add this weaker base, you end up with some nucleophile and some electrophile. And so there begins the reaction. The carbonyl reforms. It's going to push electrons out the alpha position to attack a neighboring ester carbonyl. Well, so if you think about it, in the aldol, you had a nucleophilic attack on an aldehyde or a ketone, right? When we were looking at these aldols, you had a nucleophilic attack of the enolate on an aldehyde or a ketone. Well, that's nucleophilic addition. Now, in the claisen, we have a nucleophilic attack of an enolate on an ester. That's a whole different mechanism. That's nucleophilic substitution. And the point of that is that when you have the nucleophilic attack on the ester, the tetrahedral intermediate has a potential leaving group. And what that allows for is for this carbonyl to reform and kick out said leaving group. Now, this is not a great equilibrium because we are kicking out methoxide, but you'll see what is the driving force here in just a second. So even if you make some of it, well, now look at those protons. They're not adjacent to a carbonyl, like all the ones we've seen up to this point. They are sandwiched in between two carbonyls. So they're not just activated. You can think of them as doubly activated. All right? Because these alpha protons are sandwiched between two carbonyls, they are much more acidic than they would normally be. In fact, these guys, these doubly activated protons, they have a pKa of around 11. That's pretty acidic. And certainly acidic enough where something like methoxide could come in and deprotonate. So what you end up, and this is actually the driving force of this reaction. So this, and we've seen this before, you have a bad equilibrium step as you're trying to kick out the not great leaving group. Yet, as soon as you do, you have a kind of a one direction arrow as the methoxide deprotonates those acidic protons. So this almost one direction step, irreversible step, is driving this bad equilibrium. It's just a Le Chatelier. So what that means for us is, since this is your product, all Claisen reactions will have a step 2 H+. We have to acidify the Claisen in the end so that you can isolate a neutral organic molecule. We have to give that double alpha position its proton back. All right. And this mechanism does have some specific implications on how the reaction can be run. Because this is the driving force of a reaction. If you don't have enough alpha protons, you know, if you were to do this reaction and you did not, and there, you ended up without any alpha protons here, the reaction is not going to work.
What's the point of taking it off and then just putting it back on again?
Say that again?
I don't understand the point of taking it off and putting it back on again.
Well, it's just going to happen. I mean, it's just the nature of the reagents, because you have something with a pKa of, you're kicking out methoxide, which is a decent base, and you result in these doubly activated protons with a pKa of 11. So it's not something you can avoid. It's just going to happen, because you can kind of think of it as strong acid and strong base. So they're just going to react. And when they do, you get this anion here, And so if you want to isolate a neutral organic molecule, you have to acidify it in the end to give this guy its proton back.
Oh, okay, so it's a separate step.
Mm-hmm. Yeah. So imagine for a minute, instead of doing the ester that I drew, what if we were to use this? We'll kind of go through this mechanism a little bit quickly because we just looked at the mechanism, but you would deprotonate. You would have some enolate and some unreacted starting material. This guy would attack. The bonds are a little bit awkward, but you get the idea. Carbonyl reforms, kicks out the methoxide. Again, this is not the greatest of steps because you're kicking out a bad leaving group. But look where you are now. You have this bad equilibrium leading to the condensation product. But you don't have any alpha protons here. So because you don't have any alpha protons at this position, given these substrates, you don't have a driving force, right? If you recall, the driving force of that bad equilibrium is normally, got the bad equilibrium, you make that highly acidic, doubly activated protons, and then the base that you kicked out comes in and grabs it, and that pushes, or pull, I should say, pulls that bad equilibrium towards the product. Down here, just because you only started with one alpha proton, you don't have any more alpha protons to drive the bad equilibrium. So this reaction really wouldn't work well at all. So a couple things I want you to keep in mind regarding the Claisen. Number one, as we mentioned, you've got to match the ester to the base. All right, you don't want to use hydroxide because that'll hydrolyze. You don't want to use an unmatched ester-base pair because that will lead to transesterification. So we have to match the ester to the base. Secondly, you've got to have at least 2 alpha protons. Because otherwise you end up in a situation like we did right here, where there is no alpha proton to abstract, and thus there is no leaving group. Or sorry, no driving force rather. Lastly, and we mentioned this already too, you always have to have a step 2 H+. You always have to acidify in the end. All right. Any questions on this? say that again, sorry?
So like on my exam paper like that, like there's, like the two reactions on top of each other instead of like drawing the formula from the end.
What do you mean putting the two reactions on top of one another?
Like not to be like one.
Oh, yeah, so you can, the way you would write it is just, you could, a lot of times you'll just see it written like this. Just like that, kind of like whenever you're doing Grignard reactions or hydride reductions. Okay, any other questions on this Claisen?
So we're saying that the driving force is that, for the second example, right, the methoxy or the lead
Mhm.
can be attached to the carbonyl, is that what we're saying? That's why there's no reaction, they keep going back and forth?
No, because this, normally what drives the Claisen reaction is you kick out the bad leaving group, the methoxide, but then it comes in and abstracts one of those very acidic protons in a very rapid acid-base reaction. And that, because of the difference in the pKa values between these protons and the conjugate acid methanol, this is a one-directional arrow.
Also.
So this one direction arrow, it's a Le Chatelier thing, right? So this is a bad equilibrium step. But because this is a one direction step, it's continually removing this as a product. And so as Le Chatelier would predict, if you're continually removing this by deprotonating it, it's gonna shift this equilibrium to make more of this. In this example, because of the way the substrate was, because you only had one alpha proton, you don't have any alpha protons here. So the methoxide would normally come in and grab a proton from the doubly activated alpha position, but because of the substrate that we were working with, there are no alpha protons here. So there's no driving force to pull this really bad equilibrium. So the reaction just kind of stalls out.
So it just bounces back?
Mm-hmm. Yeah. Okay, so just as we did with the aldol, you can also talk about crossed or mixed Claisen. So it would not be a great way of doing this reaction if you had were trying to use two different esters, because in a situation like this, both of these guys can enolize. And so this could enolize and attack the other ester. This could enolize and attack the 3-carbon ester. This could enolize and attack itself. Or this could enolize and attack itself. So if you did this reaction in the way I've written, you would end up getting 4 different products, and it's not a great way of doing chemistry. So we can use the same trick that we did with the aldols. The way we would prefer to do this then is just use a much stronger base and generate one enolate and then add the other. Okay, so the way we would do this, let's say we wanted the 2-carbon to act as our enolate. You would use LDA. LDA is a very, very strong base, and just like it could completely enolize the aldehydes and ketones, it can also completely enolize the ester. So we would end up with a flask full of nucleophile. You know, you'd use a stoichiometric amount of the LDA. So one equivalent of the ester, one equivalent of LDA, and you would generate 100% enolate. And then you would add in the one you wanted to act as your electropile. And there's only one way this reaction could work. Electrons go down, get kicked out the alpha position to attack the other carbonyl. You would end up with that. And then, just like in the mechanisms before, reform the beta carbonyl, kick out the leaving group. And there you have that the product in the presence of the strong base, and so that would deprotonate. There's your driving force. And then we would do, finally, an H plus step to get to the neutral product. And if you look at what you're making here, there's the carbonyl of your ester, kind of moving away from that. There's the alpha position, there's the beta position. We end up with a beta keto ester.
Arrow from the OET to the hydrogens. We're deprotonating, right?
Oh, yeah.
Okay.
Right, this ethoxide would go and grab the proton. Any questions on the Claisen? All right, well, let's do the third variation. So we can do kind of like what we did with the aldol. We could do something like this. You can probably see where we're going with this one. We've got the two esters in the same molecule. They are reasonably spaced. And so if you add base here, you will enolize. And that can wrap around and attack the other ester. Now again, like I did with the intramolecular aldol, I'm going to number these just so I don't make a mistake. And we are making a bond between carbons 2 and 7 as I numbered them. So that would make figure out what kind of ring that would make. That would be a 1, 2, 3, 4. That would be a 6-membered ring. So like before, I'm just going to draw that out and then worry about what's sticking off of it later. There's my 6-membered ring. I'm going to number this in the same way that I did the reactant. So 2, 3, 4, 5, 6, 7. Carbon 1 is sticking off of carbon 2, so you have this ester just kind of hanging out. What else do we have? Carbon 7 is the carbon that got attacked, so that should be the tetrahedral intermediate. And then the next step, reform the carbonyl and kick out the ethoxide. just like before, we need a driving force for this, and we happen to have one because you have that strongly acidic, doubly activated proton. The ethoxide can come in and grab that. And then just like before, you'll need an acidification step. To give that as your final product. And again, if you count your carbons, you'll see that this is also a beta keto ester. Any questions on this one? By the way, people don't usually, I don't really know why, but it's not that common to refer to this as an intramolecular claisen. Most people call it by the name of the person who really investigated this. Most people will refer to this as a Diekmann cyclization. But it really is just an intramolecular claisen. Danielle, did you have a question?
I did, what if the ethers on both sides weren't identical? Would you get mixed product both ways?
Yeah, you don't really see that, and you'll in just a second, and you'll see why. Just
Okay.
because of the way that these diesters are made, it would be very rare to see that. But that's a good segue. So if you wanted to make one of these diesters, let's say you wanted to do a Diekmann in your synthesis, you're not just going to be able to start there. So I want to show you how you can go about making these diesters in order to use in your Diekmann cyclization. So the easiest way of doing that is through opening up a cycloalkane. So for instance, if we were going to let's say we were if we were going to make a 6 carbon diester, we would start with cyclohexane. Photobrominate. And eliminate. What can I use here to break apart my ring? Yeah, exactly. Let's actually do it on this one. So we're just going to do an oxidative cleavage. So remember, there are 2 ways to do oxidative cleavage of alkenes. You can do ozonolysis, or you can do permanganate. Which one do I want to use here? Yeah, why?
Carboxylic acid.
Because I want carboxylic acids. So this would give me a 6-membered carboxylic acid, diacid actually. How do I make my ester? Because we don't do a claisen with a diacid, we do it with a diester. So how do I go from this diacid to the diester? Yeah, exactly. Fischer esterification. You can use either methanol or ethanol, whichever, doesn't matter. Just like that. and you're all ready to do the Claisen, or the Diekmann. Any questions on this?
So is the Diekman just going backwards over the cast? You just reform the cycle hexane.
Yeah, so to do the Diekmann, we would just take this diester that we just made. Actually, why don't you do that? And we would add the ethoxide base. So go ahead and see if you can predict the Diekmann product of this reaction here. Okay, so for this one, the ethoxide is going to deprotonate. And that's going to generate an enolate, which would wrap around and attack the other ester carbonyl. And again, I'm just going to number this 1, 2, 3, 4, 5, 6. So we're making a bond between carbons 2 and 6, which should give you a 5-membered ring, I think. 1, 2, 3, yep, 5-membered ring. With a bond between carbons 2 and 6 as I numbered them. Carbon 1 is sticking off of carbon 2, and it is an ester, which nothing happened to. Carbon 6 was the carbonyl that becomes the tetrahedral intermediate. Then reform, kick out the ethoxide. Then you would deprotonate. That's the driving force. And then just acidify to get the beta keto ester. Now, what if I had asked you like that? It's kind of tricky. I mean, in a sense, it looks kind of like the product we made earlier. Somewhat resembles this. You know, you've got the 6-membered ring with a carbonyl in the ring, but there's two differences. Number one, the product we were trying to make has a 3-carbon chain on it, and it does not have this ester. Right? But, oh, by the way, just for the record, you probably have already put this together, but the decumin, just like the intramolecular aldol, you can only make 5 and 6-membered rings. But if we are trying to make this guy, I think it would be reasonable to use that decumin product, that beta keto ester, as a starting material. Anybody have an idea of what we could do with this to start making our way towards this?
I was thinking maybe using an acetal to ketone.
You could, but you really don't have to. I mean, you could certainly do that, it just wouldn't really be necessary. Think about how we've got to add the 3-carbon chain. How can we do that? If we were to add base to this, what's that going to do? It's not going to hydrolyze because, I mean, it would if we were to use hydroxide here, but we're using the ethoxide base, which is the same as our ester, so you're not going to get hydrolysis. What do bases do? Yeah. Bases always take protons. So the question is, what's the most acidic proton? The most acidic proton by a lot is that one, is the alpha proton, the doubly alpha proton. So that's what will get deprotonated. And now I can use that as a nucleophile. I want a 3-carbon chain. Throw in bromopropane, and it will do SN2 chemistry. I'm almost at the product that I want. All right. The only thing I've got to do is get rid of that pesky ester that's hanging on. And then you'd be at the product. And it turns out this is fairly easy to do. Because if I were to take this compound, by the way, what we're doing now is what's termed we're attempting to do a decarboxylation here. So if I take this ester, any ester really, remember what happens to esters if you treat them with dilute acid and heat?
Don't become carboxylic acid.
Exactly. We're going to hydrolyze it. Remember, esters can be easily hydrolyzed in acid or in base. We already talked about the hydrolysis of the esters in base, which is why we said in the Claisen you had to match the ester to the base and you couldn't use hydroxide. Well, now we're talking about taking an ester and treating it under dilute acidic conditions. Same thing's going to happen. You're going to hydrolyze the ester. So we would end up making this. This is a very unique combination of functional groups. It's what's called a beta-keto acid. And these are incredibly unstable. And in fact, under the conditions of the ester hydrolysis, the high heat conditions that are required to do the hydrolysis, you would not even be able to isolate this. Because under moderate heating, these beta-keto acids fall apart. So under the heating conditions required for ester hydrolysis, you would, yes, temporarily make the beta-keto acid, but under the high heat conditions of the hydrolysis reaction, this thing would fall apart.
So what features of it make it a beta-keto acid?
Because you've got the carboxylic acid right here.
Okay.
There's your alpha, there's your beta. So you have a ketone in the beta position relative to the carboxylic acid. Okay. So let me show you, you're not responsible for this mechanism, but I'll just briefly show it to you. I'm going to redraw that carboxylic acid like this. It'll probably be easier. So we're just going to do like a big round robin of electrons. The way this is going to go is the lone pair of the ketone is going to grab the acidic proton from the carboxylic acid. Those electrons get pushed into the carbonyl. That's going to cause that bond to break. This bond right here is going to break. The electrons of that bond get pushed into the carbonyl and back up onto oxygen. So after this circuitous flow of electrons, what you end up with is you end up losing the carboxylic acid as carbon dioxide, hence the name decarboxylation. But what we really are interested in, follow the flow of arrows, you would end up with that. I guess that. What functional group is this now? It's an enol. Can you isolate an enol? Nope. So this thing tautomerizes. And what you end up isolating is the ketone. So it's a very handy way of, we can easily make these beta keto esters through the Claisen, through Diekmann. It gives you a highly activated proton that's easily deprotonated. You can add all sorts of stuff to this position through SN2 chemistry. Then if you want to, you don't have to keep that ester around. You can easily take it off through the decarboxylation. So it really starts to expand the synthetic repertoire, if you will. Right? We start to see how you can use a lot of this carbonyl chemistry to start making really kind of complex ring systems, a lot of stuff that you would have not been able to make previously. And by the way, I have, because a lot of this chemistry is going to take some getting used to, it's going to take some practice, and if you go to Canvas, you go into the Unit 4 module, I have something that is called this condensation workshop here. That is just a whole bunch of practice on all of this chemistry. So let me go ahead and open it up and you can have a look. The first thing that you'll notice is it has a big flow chart. And it's just kind of maybe something that you might find useful as you're starting to work with these. You know, it's just asks you questions about the structure, you can answer yes or no and follow the arrows, and kind of directs you to the type of reaction you're dealing with. So it might be kind of like a crutch you can use as you're first getting started with these. But then, after that, it just walks you through all of these reactions we've been talking about. Starting with the aldol, it describes what the aldol is, and then gives you a bunch of practice problems. Then it goes into the claisen, describes what the claisen is, gives you a bunch of practice problems. The Dieckmann, the malonic ester, we haven't really gotten into yet, but all of these different reactions and practice relating specific to those. And then at the very end, there's a section putting it all together. And that's just a random list of condensation reactions. And you have to figure out, number one, what type of condensation is being attempted, and number two, what is the product that you would get? Because that's ultimately what we're working up to. On the exam, I'm not going to tell you, give me the product of this claisen condensation. I'm just going to give you a whole string of these reactions, and you're going to have to do just what this example does, where you have to first recognize the reaction type and then predict the product of it. So this is just a bunch of practice if you want it. There's also a key for this, so you can check yourself. And then in addition to that, you can see that you have, where did it go? Condensation synthesis, and then there's extra synthesis. And both of these have keys as well. So we're not going to do, I don't think we really have time to go through the synthesis of the enolate stuff like we've done in the past. I'm not going to assign it, I'm not going to pick it up, I'm not going to grade it, but you will get a enolate synthesis problem on the exam, and so you can start practicing with that if you want to do that. And again, there's a key so you can check your work once you do that. Okay. We have about 7 minutes left, so I think that's probably enough time to do one more. The next reaction that we'll look at is number 3. The next one we're going to look at is going to involve, is going to involve these kind of doubly activated systems. All right, just like we saw with the Dieckmann, where we used the doubly activated beta keto ester as a nucleophile. That's what these next 2 reactions are going to do. This next one is what we call the malonic ester synthesis. So in terms of its functional group transformation, what malonic ester synthesis does is it uses malonic ester and it's going to end up giving you a substituted acetic acid. All right, so let's see what that actually looks like. Malonic ester is a 3-carbon diester. Looks like that. You'll notice it is one of these beta dicarbonyl compounds, just like the beta ketoester, product of the Claisen. And as a result, because it's got the alpha position flanked on both sides by carbonyls, those alpha protons are quite acidic. So the pKa of these guys with the diester compound is about 13. And so they are easily removed. So I can take malonic ester, treat it with sodium ethoxide, and that's going to enolate or enolize the malonic ester. And now I can use it as a nucleophile. It can do SN2 chemistry. So let's just keep it simple. Let's put, let's do this. Allyl bromide, the malonic ester nucleophile, the enolate, can go in and attack. Give me this guy. And then what we're going to do at the end of this is we are going to try to decarboxylate. We want to get rid of one of those two esters. And we do it in the same way that we did just a second ago. You're going to take the diester compound and you're going to treat it with a dilute acid and heat. And what that will do first is, just like we did a minute ago, dilute acid and heat causes the acidic hydrolysis of esters. So that is going to cleave both of your esters, and it's going to give you, temporarily anyway, a diacid. Well, you have a carboxylic acid, and beta to it, you have a carbonyl. And these guys are inherently unstable. And so what ends up happening here is you end up losing one of the carboxylic acid groups by decarboxylation. So we would generate carbon dioxide, and then you would end up with the rest of that molecule, which in this case would look like that. Which would look like that. So you can see that what we've got here is there is an acetic acid, 2-carbon carboxylic acid, and there is what we substituted up there. So the halide that we added up here just ends up stuck to a 2-carbon carboxylic acid. questions on the malonic ester?
So when you run into acidic conditions, it converts it to a carboxylic acid and it cleaves one of it off in like one step, or is that?
Yeah, so the first part of it, under the acid and heat, that's gonna be enough to cleave the esters to render the dicarboxylic acid compound. But under the high heat conditions, that also causes one of the carboxylic acid groups to just come off as carbon dioxide. Again, these carboxylic acids where you have a carbonyl beta to them are very, very unstable. They fall apart through just mild heating.
And what makes it malonic? Sorry, just definition.
The malonic?
Yeah,
I don't know. It's just been called that for.
but I mean, like, how would we recognize, oh, that's a malonic ester?
Oh, it's just a 3-carbon diester.
Just, so this is the only malonic ester?
Yes.
Okay.
Yeah. If you had a different, like a 4-carbon one, it would be called something else.
Gotcha.
Yeah.
Okay.
All right. I think that's probably a good place to call it quits for today. So I will see you in about 10 minutes in lab.